promise I will try to keep things not going flashy white-black. So for anyone whose eyes are a bit tired at this point, you should feel a bit better today. So again, hi, I'm Daniel. This time I'm here because my employer, Codethink, works on some software that is used in safe Linux systems, or at least we're getting there. And when I wrote the proposal for this talk, I had a big chunk of text about what I was going to talk about, and that never showed up in the agenda. So instead, I'm going to talk about something slightly different. But I promise it should be vaguely relevant. I am an ex-maintainer of RustUp, so if you've stumbled over any of the nasty corners of RustUp, I apologize. But before I get into the safety monitor, I want to give you a little bit of background about how I got here. In the beginning, at Codethink, our thought process was there are standards. And those of us who have worked in the automotive industry or aerospace or many other industries will be used to dealing with things like ISO 26262 or IEC 61508 and so on. And I already asked this morning, so I know several of you have had to deal with that. And coming on from those standards, there are ways of constraining the way that we think as software engineers to try to avoid bad patterns, such as MISRA C, Safer C, things like that. And I mentioned again this morning that MISRA Rust is a thing. Have any of you gone and looked that up? No, I'm not surprised. But all of these standards are quite narrow, and at Codethink we wanted to think more widely, which is why the Trustable Software Framework was a thing. Was anyone not here this morning in the keynote? I'm going to skip it then. Hooray. And that leads on to a thing that we're doing at Codethink, which is the Codethink Trustable Reproducible Linux Operating System. And part of that was that we wanted to demonstrate that we could use Rust on a Linux system where that Rust was in the safety path, and that it was possible to make claims about that and to talk through that. And the safety monitor is a thing that we can do that with. When I say safety monitor, does anyone here have an idea what that means? One person at the back. Hooray. At least I'm not talking completely mad. For us, this is about a piece of software that is paying attention to the system as a whole. It is measuring certain things itself. It is receiving SPIs, safety performance indicators, from other parts of the system, aggregating those, applying rule sets to them, and ultimately making a decision about whether or not the system is safe. And if it's not safe, doing something about it, triggering mitigations, that kind of thing. So we wanted to produce one of those, and we set about gathering some expectations from various of my employer's clients, including ControlOS, and trying to work out what a viable example safety monitor could be that we could then work with. I mentioned that we wanted to prove this out as Rust and open source in the safety chain, and based on that, we wanted to try to justify via Rust functionality why we were making these decisions. So that's a link to the open source project. We open sourced it in February at FOSDEM. The safety monitor is written in Rust. It's designed to work in a systemd-based Linux distribution. So we're not saying, hey, to do safety, it's got to be a really trivial thing. We're trying to go big. It uses Linux abstractions like MQs, which ISORIX would probably rather we didn't. Talks to Dev Watchdog. It's deliberately trying to be as close to an open source project that someone in the open would work with that is doing the sorts of jobs of a safety monitor. And we want, as an example, we try to minimize allocations in our critical paths, but we're not absolutely beholden to that. And we are trying to demonstrate the use of the Trustable Software Framework as a component within a wider Linux system. So with some of that out of the way, what I'm actually more interested in talking about today is some of the technical things that we're doing inside that code base. We've not looked at a lot of Rust code today, so I'm hoping to change that. If I've got the time, I might even open an editor, and we can have a little bit of a look. So if at any point, and I don't know if Sabine is going to be really angry with me for saying this, anyone wants to sort of put their hand up and jump in and ask a question about anything that I'm saying, then I would like that. Excellent. So the first thing I'd like to talk about is techniques to reduce risk. And there are 3 kinds of risk that I want to talk about today. The first is risk for your programmers and your reviewers of your code base. I'd like to show you some of the ways within the safety monitor that we use Rust to try to make it easier to work on the code base and easier to review changes to the code base. Because we are not only having software engineers make changes and review them, but we are also having people whose job it is to think about safety, looking at our changes and thinking about, does that affect our claims under the Trustable Software Framework? An association of that with that is I'd like to I'll just do one of things that we do to demonstrate how you can use Rust to offer deep interfaces for testing, because it's not sufficient for your code to be good. You need to be able to demonstrate that it's good. And finally, assuming we have time, I'd like to cover something around how we use Rust to guard against misuse of the software. So in this case, Safety Monitor is a program, not a library. So it's no good for us writing, hey, we've got these fantastic APIs that you can't misuse, because ultimately, someone is running a binary, they're supplying it with inputs, they're expecting it to behave sensibly. And so those last ones perhaps are just more suggestions for nice things that you can do with your software. So techniques to make it easier to actually write the code. Type states and multi-step builders. Hopefully all of you kind of know what they are. I'll show you some of the ways that we're doing that. Has anyone heard of static assertions? A few, OK. So we'll talk about those a little bit. Using new types to add constraints to your data that's flowing around your software. Using macros to automate code-base-wide properties that you want. And very briefly, I'll talk about atomics and mutexes. I am not going to claim to be good at this. I read Mara's book, but that's about it. So on the type states and builders side of things, Safety Monitor has an interaction with the system watchdog. So that's dev watchdog under Linux. And it's a device that you open with a standard open system call. And the moment you've done that, every X amount of time, whatever that is configured, maybe it's 5 milliseconds, maybe it's 100 milliseconds, whatever, you must write a byte to that device. If you fail to do that, your hardware will do something that you probably didn't want it to do, likely reboot. And this is used as a positive affirmation that the system is behaving correctly. If at any point you stop wanting to make that affirmation, you just stop, and the system deals with it. Typically, the watchdog is a piece of hardware that has been initialized to behave like this, and so the reboot happens outside of the control of the CPU, so it really is something that will hopefully be able to get your system back into a safe state. And to help protect the internals of our abstraction for that watchdog, we're using type states to govern what's possible during construction. So this is a trivial abstraction of that. We use a basic builder to get things up and running. Everyone hopefully is used to the builder pattern when dealing with Rust structs that you need to partially set up over time. But once we've constructed one of these things, we actually have to go through several phases of initialization, where we are building up how many handles we need within our program to deal with the watchdog, what state they're in, have they been configured appropriately for timing. And so we use simple type state construction there to move through. And the watchdog code has a whole bunch of unsafe in it, because we want to be really predictable about timing when we're actually petting the watchdog. And this approach to using type states allows us to control when we stop changing allocations. And so we can start letting things have pointers to stuff and be reasonably confident that our statements around our unsafe blocks will hold. I'm not going to jump to code yet. We might come back to that one, though. Static assertions are a fun one. Static assertions allow you to assert properties of the code itself. So you're not asserting properties of data at runtime, whether that's in tests or otherwise. You're saying, hey, I'm going to, for example, say, this type must be send. If it's not send, it's going to be a problem. But yeah, OK, you could compile your whole application and get a whole bunch of nasty error messages. It's a lot neater if when you're compiling some sub-library, you just get, hey, this assertion failed during compilation. you're not doing this right. And in the watchdog code, we use this in our petting handles. When we are starting to allocate these things, they really must not cross thread boundaries. It would be a terrible problem if there could be multiple threads dealing with these things that aren't quite ready yet. And so we use the static asserts crate, and we say that the nascent petting handles must not implement any of send and sync. And once they're fully allocated, it's fine if they go to other threads, and in fact, it would be a real pain if we couldn't hand them off to other threads that were going to do some work. So we again assert that fully completed petting handles can be passed between threads. Another one of our things that we handle in the safety monitor is allowing external programs to report in, and that external interface rather necessarily involves serializing data to and from queues. And so we can also just very trivially assert the size of things. You saw a different way of asserting sort of offsets and sizes with, I think, the ISRIX talk earlier today, and this is another way of doing that. It'd be really bad if we were twiddling with types in one part of our software and ended up breaking our external interfaces. New types allow you to add extra properties or behaviors to otherwise standard types. And I'm just going to do a really trivial example here. Within the safety monitor, we have message queues that we use for passing these indicators in. And they have really weird sort of constraints under Linux. They have to start with a slash. They have to not contain any slashes. They have to have a maximum length. There's interesting constraints around that. And our message queue names are coming from configuration. So we use a new type called sanitized MQName, which just means that everywhere else in the code that we're dealing with these things, our reviewers can trust that it's in the right format. We're not going to have to worry about it. They don't have to think about that. They can think about what's going on in that piece of code. Where if you're just passing in a string or even a path buff, you have to really think about what's going on. And so this is an example of focusing review on what matters rather than what else is going on. In the safety monitor, we have to regularly check that all of our configuration has not been corrupted. It's great if you've started up and everything is good, but when you're running, memory corruption can happen. I'm sure many of you encountered really bizarre failure cases that you can never reproduce, that should never have happened. Data gets corrupted. So over time, the safety monitor needs to check all of its static configuration and make sure that it hasn't been changed. But for reasonable, I think, reasons, at runtime, all of that data is spread throughout the data structures within the program. The configuration that a particular thread is using to decide how often it's going to poll this particular safety parameter belongs to it, not to some central data object. And so what we did with macros in the safety monitor is that we created a trait for hashing configuration data. So this is almost exactly the hash trait, but is deliberately a subset of your data. We added implementations for the standard data types, and then a derive macro that means that everything that could contain configuration data derives config hash. And it's not possible for an engineer to add new data to any of our working data structures without it automatically being picked up for regular hashing. And if it turns out that actually that was a runtime cache of something that doesn't particularly need that application, they have to explicitly annotate it and say, no, config hash is going to skip this. And so again, reviewers don't need to worry, is this something that should be in the configuration hash? They just need to notice, has it been excluded? And if it's been excluded, is there a good reason for that? So this is just one example of system-wide properties of your software and ways that you can leverage Rust to make that all work. When you design software, sometimes you have to ensure that parts of your program cannot be blocked by other parts of your program. I'm sure that all of you have written things with multiple threads, and you're probably used to using arc, mutex, foo, or maybe you're like, haha, I'm not going to share the data, I'm going to use channels to send data between the threads and so on. And that's great, but unless you're really careful when you use those, you can end up in situations where one part of your program is stuck waiting on another part of your program to complete. And when you have time-critical components, like petting of a watchdog, that can be a problem. If one part of your program causes the watchdog petting code to pause for an extra 5 milliseconds, that could be the difference between a reboot you shouldn't have done and everything working as expected. So to ensure that nothing gets in the way, we use atomics in a lot of the core watchdog, and all communications into the watchdog are done by means of that. So this is part of the internals of a petting handle. You can see a number of static items there, like name and ID. Those are values that just part of the handle. And I've cut this down. This derives config hash. There's all sorts of other stuff in there as well. But all of the information that is coming in from the outside are those atomics. State is a bit unpleasant because I'm coercing an enum into a U32. But if someone could do atomic enum for me, that would be amazing. But sometimes the utility of channels and mutexes is there. There's no reason to avoid them when you don't have to worry about the blocking. So even within the safety monitor, when timing constraints are less tight, we're using these. Channels and mutexes give you high-value pathways through your code that is using like full structured data, where, like I say, I have to coerce an enum into a U32, which always makes me a little sad when I'm doing that. I said that another thing that's really important is it's great if your code is easy to review and people can go, yes, it's perfect, but then it needs to be used. And when it's being used, it will be used in situations you didn't think about, in ways that you didn't want to think about, or it's being deliberately abused by your users in order for them to work out the edges of, how is it going to misbehave? And one of the things that we like to do with that is fault injection. If you were in the Trustable workshop yesterday, you would have seen the phrase raffia. And I'm going to attempt to expand this, and I'm staring at Lucas in the hope that I get this right. Risk analysis and fault induction automation. There we go. So users of software like a safety monitor or other pieces of safe software are going to be looking at what could go wrong, how might it go wrong, and then what they're going to want to do is to poke the software to make it go wrong in those ways and see how that affects the rest of their system. You can guess what's about to happen. We defined a trait for anywhere that you could inject a fault. You might think, oh, it would be fantastic if I could just inject a fault anywhere in the source code and life would be good. But that turns out to be really, really difficult. We looked at using Facet to give us introspection data for that, but we ended up deciding that that would involve us having to use a debugger to stop the safety monitor, walk all of those data structures cleanly, find the place that we wanted to poke and poke it. Because what you don't want when you're doing fault injection is to accidentally induce the wrong fault. Sounds a little bit weird, but if you induce the wrong fault, you are no longer able to say for certainty whether that particular problem is going to cause you issues. We tried to look at using dwarf, and perhaps like not stopping the process very long. But even then, when you're talking about something that's petting a watchdog, if you hold the process for a few tens of milliseconds, that, again, might be the difference between your system rebooting when you didn't want it to and not. So we have a trait for that. Again, we implement injection site for all of the standard data types that we can. Turns out to be a real pig to do it for Arc, because it's not particularly mutable at that point, and there were limits to how much unsafe I was prepared to shove into this fault induction part. And as with config hash, we have a derive macro. So again, all of the top levels of all of our main sections of code implement injection site, and everything within those structs and enums has to implement injection site or has to be explicitly skipped, and in our context, with a good reason. So it's another example of spreading things throughout your code base that you want by starting at the top level and just keeping pushing it down. Let's talk a little bit about guarding against the misuse of software itself. Once your software is nice for engineers to use and for testers to test, you might think you're golden. Unfortunately, you then have users who want to use your program entirely. And why are we writing code if not to solve other people's problems? So it's important to write code which makes it easy for users to do the right thing with it. These are not really safety monitor specific bits, but they're bits that I thought might be useful for people to realize that Rust helps us to work with. So we provenance all of our configuration input so that if we have to report an error, we can tell you, hey, this value that we unified with that value that came from there causes a problem because of this. Rust compiler is doing this for you. Why shouldn't software that you write in Rust do it for you as well? We don't just use new types to improve internal communication between reviewer and software engineer. We're also using them to validate inputs as quickly as possible during load. The safety monitor has a large number of configuration files because of the way that system integration works. It's just easier if you load from like 20 files if you have 20 safety services. So we want to be able to report problems as soon as we can in order that our integration engineers can deal with that more quickly. Two-stage configuration processing. Any of you who deal with large amounts of configuration, it's a really good idea to get it in as quickly as you can and as cleanly as you can, and then think about it. Data-driven programming can work even if it's only for your configuration. Offer a way to lint that. I'm doing a lot with configuration because actually Safety Monitor does an awful lot with configuration. Again, people want to integrate your software into wider systems. If you can offer a way that they can verify if they've integrated it properly before it needs to hit development boards that might be a constrained resource for testing, it's a good idea to do that. And because this stuff does need to run on real hardware, if you can, offer a way to estimate the cost of your software running. Some of these, like I say, they're not Rust language ecosystem specific, but I hope that you all think they're good ideas. So here's a quick example of the provenancing. We have in our raw configuration simply spanned data if you've used the TOML crate or marked YAML because we have our configuration in YAML. Then you get spans of where your data has come from. Marked YAML is actually my crate, so if you use that, I apologize. And if you are a Facet fan and you want to use it, please submit a deserialized implementation to me because I can't work out how to do it. New types for configuration parsing. Just like for general programming problems, we have cadences in our configuration. They're just durations. You want to do this every 200 milliseconds, every 300 milliseconds. But you wrapper around it, you write a deserializer for it, and you write your parsers. Everything's nice and neat. In your configuration, you just go, I need a cadence here, and your users will get error messages very quickly. Get all your data in. So we use two-stage configuration. Raw configurations are as close to representing the files on disk as they can be, so that if we need to report problems with that, we're very close to what the user had given to us. And then we aggregate that together by validating a set of raw configurations into a single system configuration that can then be passed around. And from then on, if you've got functions that are taking a configuration object, they never have to care, does this make sense? That's all been dealt with. So again, when you're reviewing, you can focus on one thing, and then you don't have to worry about it anywhere else in the code. Expose your linting, I've mentioned. So our validate routine can return many, many errors. Return as many errors as you can without doing the C++ compiler problem, because if your user has a 15-minute integration cycle between getting errors, if you can give them all 5 of the problems in their config straight up, it's a very good idea. Estimate your costs. How expensive is it to run your program? Particularly in safety, you need to be able to say, hey, I think actually my application is going to fit on the hardware. So that probably involves being able to report it. That may involve being able to benchmark it. And a thing that I really, really would love to see more people do is actually output how much this is going to cost on the system that you're executing on. We use that in our integration testing to verify that when an integrated system has all of its different bits of safety applications and all of the configurations that they've put in, is this likely to overflow the amount of CPU resource that we would like them to have? In traditional safety with static analysis of all of this, that's fantastic. Under Linux, we have to be able to work it out later. So hopefully at least some of that has piqued your interest. If you're interested in trying out or taking part in any of that, then the Trustable Software Framework, just some links again for that because I would be shouted at if I didn't. Ditto if you're interested in the safety monitor. On the left there is some of the documentation. Feel free to look at that. And on the right is a link to the Git repository. At the moment, it's on gitlab.com. It is hopefully going to move to Eclipse at some point, but I'm not entirely sure about that one. So I'd like at this point to ask any questions.
Thank you, Daniel. Are there questions over here?
So great talk. 2 questions. One on the config hash. Does that also then create functions for validating that the CRC or your hash over the stuff is correct on access, or do you explicitly need to do that yourself when accessing the thing? And the other one, I would be really curious if you could show a sample of how you would inject one of those errors.
I'm going to try and... Whoa, I've lost my...
Can we get the slides back?
Can we get the slides back? Thank you. I'm just going to try and get something that's big enough that you guys can read it. How's that?
Can we read that? Yes.
Yep. OK. So... No. So the config hash stuff is just about the computation of the hashes. But we also have, and is Rust Analyzer finished? It has. So within the safety monitor itself, we have an aggregator that has registered with it every one of these top-level objects that can produce hashes. So we have this thing called a proc file watcher. We have service monitors. We have extrinsic indicator processes and so on. All of these are separate threads, and so they're having to do their own work and report back. And the config hash aggregator is the thing that over time, let's see if I can find you the relevant code here. Yep. So over time, it is waking up. It's scanning through all of the handles. It's checking that they've been updated in time. It's checking that it then adds all of the hashes together. It checks its own hashing, reports all the way through, and hopefully doesn't ever tell the watchdog to fail. So that's kind of how we handle things with the config hash. And if I jump back up towards the top of that, you can see, for example, that there are parts of this that say, OK, to hash this thing, we're going to have to call this extra function because that's not something obvious to do. There's a fault injection site skip because it's a pain to do it through a vector, through the arcs rather than the vector. You can see that we're skipping our watchdog handle. Yeah, this is kind of how it's used in practice.
Any other questions? No. Any questions you had from Daniel from this morning's talk?
Yeah. Anything about TSF or anything at all?
No. No. OK.
OK, thank you.
Thank you, Daniel.